Okay, so we're pleased to have Spencer Breiner from the National Institute of Standards and Technology talking about 7 scribbles in applied category theory.
All right, thanks for the introduction, David. Okay, so today's going to be a peek into my brain and the madness that lies within it. It was a very hard talk for me to prepare because I have sort of too many things that I want to talk about, but not enough to say about any of them to fill up a whole lecture. And so I've decided to just give you all of the things in my brain and a little bit of each one. Now, that said, I think that most of the time my work is kind of boring, and so I'm mostly going to talk about other people's work with some sort of small tweaks and additions that I've seen. And I really want to encourage people to take anything you see that you find exciting and use it, improve it, write it up, because I'm not going to have time to do it anytime soon, and I really want these ideas to get broader traction. And so finally, thank you again to David and Brendan and the rest of the Topos Institute crew for putting together such a wonderful, fantastic place, and for me to have an opportunity to give a talk in person to mathematical colleagues where I don't have to sort of hide the brilliance under the bucket. It's really nice to be here. Okay, so I'm going to start off talking about some sort of reasonable NIST things to think about, like geometric product specification and measurement, and then we'll sort of descend further and further into the depths of my brain, looking at simpler and simpler things. So perception's still pretty hard. Analysis is college level math. Calculus is college, high school level math. Sums and products, elementary level. And then at the end, I'll come back and try and say a little bit about flourishing, because I'm really excited about Topos's mission here. Okay, but first we're going to start with geometric product specification. So this is, at least as far as I'm concerned, this is a body of standards developed by the International Standards Organization. And so to sort of start off, when you sort of are creating some sort of new physical object, the first thing that you do is you design it. You say, what should it look like? What should its shape be? And then you send those designs off to some plant, and then it gets manufactured. And then the manufacturer needs to run some tests on it in order to check that it actually conforms to the specification that you gave it. And so the GPS standards look at these two pieces, and they sort of ignore the manufacturing process in the middle. So they say, how are you supposed to specify these designs, and how do you test them once they've been realized? And to some degree, we can think about this as a syntax for the design, and then this is some kind of semantics that it's expected to satisfy. Okay, so now here's an example of what such a piece of syntax looks like. So this is the notation for a profile surface texture in this body of standards. So that's ISO 1302, tells you what this thing's supposed to look like. And so each element of this sort of notation tells us different pieces of information. So 8 right here, the fact that this is a triangle, tells us that we're removing material. This tells us that we're looking at the profile perpendicular to the sort of grain of the material. We're looking at an upper limit and a Gaussian filter with various cutoff parameters. This tells us how to compare that, the number that we get out of that analysis, with the limit that the designer has set. So 3.3 millimeters, I think in this case, is the limit here. Okay, so now, so that's sort of the syntax side of things. And for the semantics, I'm just going to draw a picture. So the way this actually is not the way they do it anymore, but this is the way they used to do it. So you've got your sort of you've got your sort of zoomed in picture of your surface, and what you're going to do is you're literally just going to take a needle like this, and you're going to drag it across. And as you do, you're going to sort of keep track of how high up and down it is, and that's going to give you sort of a curve that's going to tell you what the profile looks like. And then you do some sort of filtering on the low end and the high end, and then you check that it satisfies this condition. And so now, unfortunately, this stuff is not all in one standard. So in ISO 1302, they tell you what this symbol looks like. And then there's 4287 where they actually tell you what all of these notations in here mean. And then there's 4288, which tells you actually what this max means, which is how you compare this number with the things that you're supposed to get out of those notations. And so that's just on the syntax side. Then over here on this side, they need to tell you what is the measurement process, so that's 3274. They need to tell you about the equipments, that's 5436. They need to tell you about how to calibrate the equipment, that's 12179. And so there's this whole body of standards that are all sort of interconnected. And so they've got this matrix model, another standard, ISO 14638. And so what we do is, so we were just talking about profile surface texture there. But there's actually like a dozen or more different kinds of characteristics that a geometric product can obey. So there's profile surface texture. Aerial surface texture is where we're not looking at a slice, we're actually looking at an area. You've got things like cylindricity, perpendicularity, parallelism, sort of all of these kinds of things that your designers want to be able to specify. And now we need some rules about how it is that we check that what they specified is actually what you're going to get. And so roughly we can sort of break them down into specification, measurement, and then there's also always the comparison in between. Okay, so now that's sort of between the standards, but now we can go inside the documents and there's so much more structure, right? So the scope, whether it's specification, comparison, or measurement, okay, that always shows up in section 1 of these documents. In section 2 of the documents, you have references to other standards because it's a whole body of standards. And so they're at least going to tell you, oh, you need to look at this one and that one and that one, so on and so forth. Okay, so now in section 3, they give you definitions and terms. And what's interesting about these definitions of terms, of course, is that, first of all, there are references within documents. You need to say, sort of, what are you pointing back to? And there's also references between documents. And so we've got some kind of like vibration-y thing here mapping down, right? Because if you have a reference, then you should certainly have if you have a sort of textual reference, then you should have a documentary reference. Okay, so let's see. So what are our goals? Okay, what are our goals in this kind of a project? Well, we would really like to make it easier on the people who actually have to write the standards, because we're the people who have to write the standards. I'm not, but people who I work with are. Okay, and so, right, we really don't want to allow anyone to stick one in here, because then, oh no, I've got a circular definition. And so if I want to look at things like circular definitions or redundant definitions in this kind of a context, I really need to have all of this information, right? It's not enough to look up here, because it's okay if there are circles, right? I can have some virtuous cycles between the documents that don't cause any problems, but I need to be able to recognize that sort of inside the document. And so our goals here are sort of to expose the combinatorial structure that's within and between these documents, mostly, as I said, to support standards development. So right now, no, I'll get to that later. We'd like to do some automated analysis. Another thing is change propagation, right? So these things get edited periodically. And so you would like to sort of make a modification here and then say, at least know what you need to look at in order to change, right? Even if you're not going to do the changes for someone. Okay, so now geometric product specification. So now I'll move on to measurement a little bit. This is another standard from the same body, though, so there's a little bit of continuity here. So in ISO, so there's not just these matrix models, not just these guys. Not just the matrix model, so there's also sort of another dimension. So the matrix is two-dimensional. There's also foundational standards that describe how the whole body of standards works. And so one of those is this ISO 8015. And so inside there you get this definition of what's called the duality principle, which organizes the relationship between designs and tests for all of the standards. So it says, right, so first of all, specification defines a specification operator independent of measurement, right? And so somehow this thing is supposed to live all by itself. The operator, incidentally, you can think of that as somewhere we're relying on a free category, right? We're saying we've got some GPS specification processes that are built up in terms of chains of operators. And then the second part says that the specification operator is realized in a verification operator, which is independent of the GPS specification, but is intended to mirror it. And so, well, I don't know how they read it exactly, but the way I read it is that we have this notion of a test that's sort of independent of whatever design you're thinking about. And then what we're really talking about is verification itself as some kind of a structure-preserving functor like this. Okay, so let's see. Yes. No, I'm not ready for that yet. Okay, so now this brings me to what I call the other Paul Scott conjecture. And you might have thought that we were parenthesizing it like this, but you would be wrong. we're actually parenthesizing it like this. So Paul Scott is the guy who he's been working for 10 or 12 years pushing category theory. He's an engineer from within these technical committees that run these ISO standards. And so he and his students have done a lot of work trying to formalize what's going on with profile surface texture in category theory. And so it was really working with them that we sort of got into this whole business. And so the other Paul Scott conjecture says, and I should really wait on this, but I won't. Where did it go? Specification and verification are, and I don't know if he would be quite so blunt, always related by an adjunction. Right, so over here I told you that we have one structure preserving functor. And what he tells me is that really we should have one going back in the other direction as well, and that they should be adjoints. And so the place that this comes from is back over here. So let me redraw this guy, because it's not quite right. So when we really do this, what we do, or when we model it at least, we assume that it's a circle. And so it's going to have, or a semicircle, and it's going to have a radius r. And so that's what we're going to pull over this surface. And so if you think about what's going to happen, well, we're going to track really the center of the circle up here, right? And so if you think about what's going to happen, it's going to do pretty good up here. But when we get here, it's just going to dip down a little bit, right? And then similarly, like here, we'll jump up a little bit early and go down a little bit late. So everybody sort of see why that is as you're dragging this circle across? OK, but of course, this is not the profile of the thing that we want. It's like, however, it's r distance above the thing that we want. So what we really need to do then is take that thing and push it back down, right? And so then we get something like this that sort of, I may not get these pictures exactly right, but it's something like that. And so then what's going on here? So if we have some domain contained in R squared, then we can talk about the dilation of D by R. Right, and that is just the union over all the x in D of the ball centered at x of radius r. Right, so we just take the unions of all of those things. And so if we sort of started with the downset of this guy, right, and we did that, then we would get this thing up above. And then there's also the erosion of D by r. And well, I'm just going to sort of do it in the easy way. Right? And so once I've done it like that, some people already see that we've got an adjunction hiding in here, right? And so let me make sure I get it right. Well, really, I should probably put like an interior here if I want to work with open sets, which I do. So we've got like O of r squared and O of r squared, and we've got dilation and erosion. I'm going to sort of drop the r, or parameterize it or something like that. And so it should be the case that if the erosion of, let's see, x by r is contained in y, then x should be contained in the dilation of y by r. So this was sort of the first thing that Paul and his students found that sort of hinted to them that there was this adjunction going on. And I mean, it's important, right? This is literally what's going on when they're doing these analyses, is they literally are pushing it up and bringing it back down. And you're getting the co-unit, or the unit, must be the unit, right, is going to say that this function is less than that function, right? And so we get an upper bound. And so it's not just trivial. OK, so now perception. Let's see. So a little bit of background on this. Okay. We're really starting to descend, aren't we? OK, so and the way I sort of think about this, at least right now, is you start with measurement, and then you add some dynamics, and then you get perception. That's probably reductive, but it's a start. And so my background here is that I've been interested in something called active inference for a while. So this is an idea that's been pushed by Carl Friston, and I think some people around here have talked about it a little bit. And it's supposed to be some biologically plausible, unified mechanism for how perception and action work in the human brain. And so Carl Friston is this like famous multi-mega citation guy because he invented the idea of using voxels to study brain states. And so he's got like billions and billions, and then he got into statistical modeling somehow. And so now he's got this other thing that's it's big, and it's sort of all represented in probabilistic notation, which you guys probably know is a mess. Brendan can maybe tell you about my rant about probabilities someday. So I went down the rabbit hole and like I'm trying to understand predictive coding, which is the version you get when you're just doing perception and not action, and information theory more generally, like what the hell is going on with all these logs. And so I was really excited when Toby Smythe put out a paper in 2019 and then again in 2020, sort of trying to put together the pieces that we need in order to do this active inference. He's also coming from neuroscience, so hopefully he understands all that stuff better than I do. It's still too hard, way too hard. And so it's apparently well known in this area that if you restrict to sort of linearity and Gaussian probabilities, then you get Kalman filters falling out. And so Jules Hedges told me he wanted to understand how Kalman filters sort of fit into this whole story, and I haven't figured that out, but I've been thinking about Kalman filter. Okay, so I better go through this pretty quick, which is a little bit sad, but it's not too bad. Okay, so what's going on? So the idea here is that you've got some kind of an agent who has a state in the world, so position and velocity maybe, and then you have some kind of way that their state is updating, and then you also have some observations that they can make about the world. And so based on those observations, they're supposed to update their state and sort of keep track of where they're at. Okay, and so let me see if I can get this right. So I'm just going to sort of, I had this up here because these boxes of numbers and symbols always terrified me. And so this is like one of the things that I love most about category theory is that I can take these like matrix nastiness and just like unwind it and unwind it and unwind it and finally get something that I can sometimes understand. Yeah, go ahead.
Sorry, in that second formula in the second P, is the second instance of k minus 1 supposed to be a k minus 2?
No. So that's coming from the fact that there's two different kinds of states. So basically you can predict if you don't get an update and you can predict if you do. And most of the time when people do this, they sort of do one of these and one of these and one of these and one of these. And so they sort of build the whole thing together into one loop. But there's nothing important about that. You could do like 15 of these and then get a message and do one of these. Yeah. Okay, good. So, so now what have we got? What are the pieces? Okay, so we have this X, which is the state space. And you should be thinking about this as sort of the set of positions and velocities. That's sort of the thing you want to have in mind. And then you've got some F that goes from X into X, which is like your state update. And so here, really, I should be putting like these things. This should be something like 1 delta t 1 0, right? And so in the Kalman filter, classical Kalman filter at least, everything's linear. I'll say a little bit about sort of relaxing that assumption at the end. Okay, and so now, so our state update then is going to look like this. So we have some x, and now we're going to go to fx plus now epsilon, where this is some kind of multivariate normal positive. So you can associate with a positive semi-definite matrix if you want on the appropriate dimension. Okay, so then, okay, so when we're now, so once we do that, then sort of our state estimation should be of the form that sort of x is a normal on some kind of mu sigma, right? So once I've sort of told you that my update is probabilistic, then it's sort of hopeless to expect that I might maintain a precise model of where my state is. And so the sort of, at each point, the state estimation that your agent is going to maintain is a normal distribution, right? So you maintain both where you think you are and sort of what your covariances look like around that. Okay, and so now we need to tell you how to update that. Okay, well, if I start with mu, then I'm just going to send that to f mu. And so somehow by linearity and the fact that we're just using Gaussians, everything else cancels out. And your sort of best estimate of your state is going to just be to apply f. But then we also have to tell you how to update sigma, right? And so what we're going to do is we're going to take sigma, and then we're going to do f. And let me get this right, because otherwise my diagrams are going to break. Let's see, where is it? F transpose F plus, and now, where did it go? Oh, I've used the same symbol for two things. That's bad. Let me call this one, guess I'll call it Q. OK, so that's this right here. I'm using different notation, which definitely isn't helping you guys. But you can see the conjugate, right? So P is my previous state. I'm conjugating, and then I'm adding on some noise, right? And so, right, so sigma is my estimate of my current state. Q is the noise that gets added on from my, right, I guess this is my epsilon. I'm sorry, I should just call this epsilon. Right, where now I'm really thinking about this as a covariance matrix, not a probability distribution. OK, so now what's going on here? Well, hopefully at least some of you guys have seen state process duality and transposes in the diagrams of matrices, because I'm going to go through that pretty fast. So the idea is sort of when we're working with matrices, we often want to think about them like this, but sort of for free, we can turn them around and just have a state that has two things coming out, right? And, well, I won't explain why that is, but we have this thing, right? It's compact closed category. It's that kind of lingo. OK, and the other thing is that if we have some f, and we flip around both of its pieces, and we draw a box around it, and then the thing on the outside is F transpose, right? And so now we're starting to get some hints about how we can unwind what's going on over here. So now if I use this and I try and write down that equation over there, then what I get is something like this. So first, right, and of course you also have to remember that in this whole thing, stuff comes in from the right, right? And it's like, additionally, we've got this. So F transpose is the first thing we do. And then you do this weird thing with your state estimation. And then you pipe the result past F. And then, OK, well, since I want to think about things as states rather than matrices, I'm going to flip that thing back around. And then I'm going to unwind, right? Oh, thank you. Here's my sigma. I should have written that in there. Sigma, whew, F, F. OK, well, that's a lot easier. OK, so now what about this epsilon? OK, well, I told you it was a positive semi-definite matrix. And so again, with this trick, we can do the state process duality and stick that guy out. And now sums are really, well, we can model sums using a Frobenius algebra in this story. And so what we're going to do is we're going to take plus and plus, feed that, oh, not that one, feed that one in, feed that one in. And there's our state update. OK, well, that's a little easier, I think, at least. OK, so now what's going on with observation? OK, well, this one's much worse. Not that much worse. It's not that much worse. OK, so, but it's the same kind of story. Let me just get rid of these guys at the bottom. So what else do we get? Well, we get this O, which is our observation space. And we get an H that goes from X into O. So this is looking very familiar to David now, right? We've got our outputs here. Perfect. OK, and so now I'm not going to sort of go through and draw all the pictures, but you can see we do the same thing, right? So there's our sigma, it's P in the middle, and then we do this H transpose H business. Well, we just figured out what that means. Then we add that thing. OK, well, that's looking pretty good. And now, so that's S, and now we're going to take the inverse of S. And I'm like, oh, no, I don't know what inverse means. So I just take the dagger, and I feed that in. And I think we've got one of these things where if we take something and multiply by its dagger, then we get like the norm squared. And so we should be able to just divide by that scalar if we're in a context where we can do division. So hand wavy, obviously. OK, so we did that. And then we feed that through H transpose. And then you feed that back to P. That's our sigma again. Oh my God, what the hell is going on? OK, so now for our next covariance matrix, we're going to take the identity and we're going to subtract off that thing that was the inverse multiplied by that other stuff, and then pass it H through again. And then we're going to multiply that by our original guy. OK, my God, what the hell is going on? OK. But this is why we love diagrams, right? OK, so here's what's going on. So we take sigma, right? And now we're going to take one of the guys and we're going to copy it off. This is that I minus a bunch of other stuff, right? Because we're feeding it off and then we're feeding it into a plus and we're feeding something else into a plus and we're sending the sort of the remainder off in the distance. And so then, right, here's that stuff that we just did over here, only we're doing it with H's and O's instead of with X's and X's. And then we sort of do this again. And why we do this, I don't know, but I'm just sort of copying off the Wikipedia page. I'm pretty sure that there's more simplifications to be had. I sort of didn't have enough time to create this talk, as you guys can tell. So we've got a plus Frobenius and an equal Frobenius, and we know that we've got this hop algebra here. So the next obvious question is, what do you get when you pass that through? But I haven't had time to think about it. So please, someone think about it. OK, there's also the CPM construction going on here. So that's the thing where you do this doubling, where you sort of take two versions of a category and then you sort of fold them in half. It's all in Koch and Kissinger's quantum mechanics. So because this guy is positive semi-definite, you can factor it into a product of something in its transpose. And so then sort of each one of these guys is actually a double, and you can kind of see that everything's double, 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 double. And so it probably becomes much easier to draw if you actually just do all that folding, but I didn't. Whew. OK, so now just to close out on that line of thought, so the extended Kalman filter is what you get when you drop the linearity assumption. OK, and so then you get something that starts to look like this. So I've got an X coming in, and I copy it off, and I do my F, right? And then I pop this guy off, and then up here I've got something like a dx tensor dx. And then I'm going to feed that into df, right, and get out my new, I guess, really df tensor 2, tensor dx. Right? And so now what I'm really curious about, so we've got sort of two different versions of this story now, where one of them is this kind of quadratic version where everything is infinitesimal and we're just maintaining this covariance matrix up here. And so now, why do I have, right? So we've got some kind of update when we do that, right? And that's what Kalman is doing literally. Or sort of, that would be the most naive generalization of the linear Kalman that I did. But we've also got this sort of probabilistic semantics that we're interested in, where these things actually represent probability distribution, normal distributions over these spaces. And we also have some notion of updating over here, but it's sort of no longer exact, right? And we don't get Gaussians out. And so what I'm really interested in is sort of, can we control the error? Right? So it should be the case that as long as our covariances are small and our second derivatives are small, for instance, then we can apply the linear correction to the normal, and we know that we're sort of not too far off. Right? And having some kind of control over the bounds of that error would be really interesting. OK, how am I doing on time?
It's 5:05. So.
It's what?
It's 5:05.
5:05. OK, great. Perfect. All right, well, that's good. I think. OK, let's see. What should I get rid of? Let's get rid of this stuff. OK, so some dx's showed up over there. So now we're changing topic. We're going to talk about analysis. So I've already talked to a bunch of you guys about this already, so maybe it won't be that exciting. OK, so let's see. This line of thought for me was sort of all kicked off by a recent paper of Bosso, Bonci, DeGiorgio, and Sobocinski, this diagrammatic polyhedral algebra paper in ACT this year. And so what they do, so I'm going to kind of assume that you guys are more or less familiar with the general graphical linear algebra story. And so the way it goes, right, is we've got these sort of spiders for the plus guys, right? I've basically already been assuming you know this because I've already used all this notation. We've got sort of another spider for the equals. And these guys have some kind of hop relationship. And OK, so that, oh, right, and we've also got A for constants in some scalar ring field, whatever you like.
The plus of the left wires equals the plus of the right
That's right.
wires.
That's right.
And the equals mean they're all equal.
That's right. That's at least how I want to think about it. Probably you don't have to interpret it that way, but I don't know for sure. OK, so
It just means there's a negative. There's a symbol for negative.
I actually didn't even mean hop. I meant like the bimonoidal. But I think they want the hop stuff too. It's like there's a lot of rules. I can't remember them all. OK, so you get this, and from this you get like linear relations or something close to it. You need lots of rules too. And then they add this new guy that's basically a 1. And this one gives you affine stuff. That's cool. And then they add an ordering. And this is what gives you polyhedra, right? And so here we can see that going on. Right, so there's some kind of normal form. And I don't know why they have the m coming in. If it was me, I would have the m just coming out. So there's a normal form for things with n in and m out. And it says you can always represent it as sort of some matrix that takes m plus n inputs and has p outputs. And then what you're going to do is you're going to add that to B. All right, so that's some affine plane. And now you're going to say that that thing is greater than 0. Right? So, well, that's a half plane. Sorry, that's not a half plane. That's a intersection of half planes, which is a polyhedra, at least as long as you allow like infinite ones. OK, so that's cool. And then they had this like research paper that they did on Zulip where they, so I don't think this is quite right, but there's something for sure going on here where they added another piece, which was a diode, and they got piecewise linear. At least they think they do. I don't know what the current status of that conjecture is. But in any event, they drew this diagram for the boundary. And so, OK, this kicks me off on thinking about what I was doing in 2005 here at Berkeley when I was finishing up my undergraduate career. And it was basically my first experience of real research mathematics. And it was so exciting to me. So Jenny Harrison is now emeritus up here. She ran a grad seminar on analysis on basically the foundations of differential forms. And she was coming at this from Plateau's problem. So that's like soap films. And so there you have these problems where your soap films can make shapes like this. And you guys were just talking about problems like this. So that was nice. OK, so the usual approach to doing these kind of domains is that you start with some kind of simple ones like intervals or squares or something nice. And then you define how to integrate over those things. Right, so you say I can integrate functions or forms of the appropriate kind over these simple domains. And then you stick the simple domains into the double dual in order to get sort of richer domains like Dirac deltas and fractals and sort of all the kinds of other interesting, neat stuff that you might want to do. And so, but there's a different, so apparently you get a lot of cruft when you do this too. I don't have any real examples, but there's like a bunch of stuff in there that maybe you don't actually want to think about as a domain. And so there's an alternative that comes up. It's sort of related to, I think it's called Whitney's extension theorem or Whitney decompositions. And again, you guys are talking about these like mesh refinements. It's like right here. So instead, what you do is you actually define so you define a norm on your simple domains and you complete. And that sort of gives you your space of rich domains. And then you define functions and forms as duals to that. OK, so it's like your functions are really functions from the domains into, and that's like the integration of a function over that domain. OK, and so when you do that, you get Stokes' theorem for free, which is nice. Right, so if you want to say the integral of df over x is just defined to be the integral on the boundary of x of f. And so so what's really important here now is that the boundary needs to be continuous. So for this whole story to go through, the boundary needs to be continuous, because otherwise this guy's not going to be continuous. And that would be bad for you for some reasons the analysts understand. OK. As well as some other things. So like also you want Hodge star to be continuous and some other sort of nice machinery. OK, so in this class that she taught that I loved so much, you start out with some simple domains that are polyhedra. OK, well, that's pretty good. Because we sort of just talked about how to do polyhedra over there. And they have to be oriented polyhedra for one reason or another. And so, right, we can take the boundary of P plus, and it's all topological vector spaces, so we can add things together too. So it's really sort of like you can add these guys together, and now it's sort of like twice as heavy right there. OK, and so now if we look at the boundary, right, so let's sort of give these guys some orientations. Then I guess, right, it's going to be this guy. And, right, just point the opposite directions. They cancel out. OK, well, that's good. But it's kind of bad news for our continuity, right? Because now suppose we took P and Q, and we separated them by some distance, and we took one parameter family and sort of moved them together. And so the boundary, well, it's just going to be a couple of squares, right? And I guess the point is it's just going to stay a couple squares and stay a couple squares and stay a couple squares until they touch, and then those intermediate pieces are going to annihilate, and there goes your continuity, at least maybe. OK, so what she did is she defines a norm on the space of polyhedra, or sort of like subdimensional polyhedra, really, because we have like one-dimensional subsets of C2, of 2 dimensions. And so what she does, where is it? There it is. So we say that the norm of sort of a naive polyhedron is going to be less than or equal to its area. So we sort of have one place where we start for the actually simple things. And then we're going to say that if D is equal to the translation by some vector of E minus E, then the norm of D is less than or equal to the norm of V times the norm of E. Okay, and so now when we take these two guys, and we move them closer and closer together, they're oppositely oriented, so they're negatives of one another, and their distance is decreasing, and so they're going to smoothly go to 0. The norm is going to smoothly go to 0 as they collide. OK, and so one thing that I sort of wanted to call out here is that notice how kind of co-algebraic this statement is. It says your norm is defined by all possible decompositions of a certain sort. Maybe that's not co-algebraic, but it feels co-algebraic to me. And I still sort of very much want to understand what's going on with co-algebra and calculus. OK, so let's see, do I have anything else here? Right, OK, so we've got here's some pictures of these difference chains, right? And so the idea is sort of, even if this area is very large, the norm of the sum of these things could still be very small. OK, and so now you get a nice norm in this thing, and you can complete, and then you show that you get the right functions and the right forms. So that's sort of one piece of this story. And basically, as I was taking this class, she found out that you could start with a different class of simple domains and get to the same place. So these polyhedra are very nice because they're sort of easy to think about, and they're macroscopic, and we can understand them very easily, but they're hard to compute with, right? When you want to think about all possible decompositions of this infinitary thing, that sounds like a pain. So what we can do is we can sort of like take this thing and squeeze it. So rather than just making it smaller, we're going to make it smaller and also increase the weight sort of as we go, right? And if you do that, you can sort of see, right, that this is going to be a Cauchy sequence, right? Because I have sort of 4 copies here, and I have to translate this one a little bit, a little bit, a little bit, a little bit. And sort of as I go down this sequence of sort of smaller and smaller and heavier and heavier squares, the translation between, right, it's sort of like I'm comparing this guy with this guy, right? And so there's sort of like, I translate 1 copy here, 1 copy here, 1 copy here, 1 copy here. The vector of that translation is proportional to the length of the side of the square, so it's going to go to 0. And so you get a Cauchy sequence, and so now you get something sort of out at the end that's this little infinitesimal Dirac delta, right? That is the Dirac delta you wanted, and it has a boundary that's also infinitesimal, right? And so you have like little tiny dipoles and quadrupoles and all kinds of other crazy stuff that live at the points. And so now you can describe the sort of space of simple guys that you start with and attach your norm to as finitely supported sections of the exterior bundle. And so that's sort of a very finite computational thing that you can get your hands on. And when you go to look at all of these decompositions, you find out you're looking at something that looks very much like an Earth-Mover distance, because you can sort of take some combination like this that aren't far apart, and you can kind of break this one up into a sum and translate them in different directions. And you break this one up into a sum and translate them in different directions to cancel them out. So I don't really know what that means, but I know Evan's interested in that stuff, and so I wanted to bring it up. OK, so that's analysis. Oh, right. So back to Pavel's stuff. So all of this graphical linear algebra stuff that got us the polyhedra and that got us the piecewise linear polyhedra, which is exactly what we need for these simple domains. So it's all formulated in this bi-category of relations kind of stuff, right? And so the picture you should have in mind is that this is less than or equal to f. Right, and so that says if I run f and then I copy the output, then I could have gotten that by copying the input and running f twice. But if f was non-deterministic, then maybe I would have gotten different things out here. And so this one is always contained in this one. And so in all the stuff that I've been brave enough to read about, sort of everybody's treating this as just a Boolean, right? It's either true or false. But as far as I know, there's sort of no obstacle to putting some positive real numbers in there. And so now we're like extremely close to having norms and having analysis fall out of this stuff. And so I'm gonna leave it there. Hope somebody else picks it up. Okay, analysis. Okay, so the next one, right, we're going down, we're getting simpler, so down to calculus. Okay, this one really I don't actually have anything to say. I just want to call it out because nobody ever told me about this stuff, and I don't know how that happened. So did everyone know that in Penrose's work he had these bubble notations for derivatives? David's the only one who knew. How is that even possible?
I learned recently.
Me too. I learned it from this paper that came out in January.
I think I learned it from you.
Yeah, probably. I've been telling everybody I can. So, I mean, you can't really tell what's going on in that slide, but let me see if I can. So this is Kim, O, and Kim, and they're sort of very focused on pedagogy of vector calculus. And I like that about this work. So here's their description of the cross product. Clank, and the sign changes. I love it. OK, so how does this work? Right? So you've got scalars. So you draw those like f. You've got vectors. So they use like a with a line coming out. So this all looks pretty familiar. So the dot product is the cross product is this other one that you see over there. And then there's the derivative, directional derivative, nabla. Right? And so it looks like this. And then sort of you're supposed to put the thing that you're taking the derivative of inside. And this one is supposed to tell you the direction that you're taking the derivative along. And so, for instance, if I put a in there, then somehow if I put an I on there and a j on there, then that would be daj dxi, right? OK, so cool. And then you've got, they don't really get into it quite enough because they don't go up to tensors, because as I said, they're focused on sort of very pedagogical material. But you should have something like a Leibniz rule, too, that says a b equals now let me get it right. I think this is OK because I should be able to permute them. But it's possible I may have missed a negative sign. As they don't go into this stuff, so these may need to be anti-symmetric tensors or something. I don't know. In any event, there's going to be some kind of Leibniz rule that's relevant for this this notation. No. So this would be a tensor. So that's why they don't really talk about this, right? Yeah. And so OK. So now did I put this on the? Yeah, because I didn't want to have to draw it. So now we get vector calculus identities, and they just fall out. You can just follow your nose. It's like, could anybody ever remember this? No, I couldn't. I had to look it up, and I'm still not sure I got it right. But modulo some additional concern about how exactly you're doing the transposes and the negatives, this is the kind of thing that I can remember. I like that. And there's a bunch more in the paper, sort of all of the standard vector calculus identities that you go through, and they do them all in like 12 pages. Yeah, that's this guy. Yeah, and so somehow, right, cross products suck. Who wants to use cross products? Really, we should be looking at like wedge products, and probably everything would be nicer if you did. OK, so calculus, I think that's about all I had to say about that. But like, we should be promoting this. Everybody should know about, everybody who knows about string diagrams should know about this, at least to a first approximation. OK, so now Sums and products. OK, so sums and products are like the bane of my existence sometimes. Poly is getting some direction towards getting it worked out. But really, I'm mostly talking about in this matrix case, right? Because graphical linear algebra, all of that is expressed in the sums. The Koch and Kissinger work, it's all expressed in the products. And like trying to interpolate between those is beyond me. I'd rather not have to do that. And so somehow we really need better structures for handling both of these things together. And so that's actually, I wasn't supposed to show you this yet. Did I forget to do it? Oh, there we go. That's the one I want. OK, so this is from Comfort, Delpouche, and Hedges' sheet diagrams for binominal categories. Came out, I think, towards the end of last year. So these are a couple of different kinds of notations that people have used to represent this. And so what's going on, so this is the one they use in the paper. And so what's going on here is sort of the tensor is going on within the sheets, and the sum is going on between the sheets. And so it's kind of the same thing going on here, where you think of sort of like each one of those guys going. And really what we need is some computerized interfaces for dealing with these, because really what you want these kind of to be like stacked on top of each other. So you can only see one of them at a time, but it like forces you to make sure that you handled all of the cases. OK, so they do, this paper is very nice, but the reason I want to bring it up is because I thought that there was a little bit of a missed opportunity here. OK, so maybe, well, yeah, I'll skip all that stuff. OK, so CDH, these guys, so they use distributivity to get a normal form on the objects. And so what that means is basically they are splitting things out into as many sheets as they can go. And normal forms are very useful, obviously. And this is helpful for sort of reasoning about things. But it's bad if you want something like computational efficiency, because if you've got lots of copies on those sheets, then at least if you do things in a naive way, you're going to sort of do them over and over again. And I think there's also maybe some other more interesting ideas lurking here if we extend the notation a little bit. OK, so in the work that they've done, right, so everything looks kind of like this. And so there's like, right, and so there's like two sheets coming together, and maybe there's some stuff on this sheet that comes into some map. They just use dots because it's easier to do things if your maps are zero-dimensional, right? But they don't have any vertical seams. And so and that's really coming from the fact that they've done this normalization beforehand. So so now I'll go into this other picture. So if you think about sort of not normalizing, then you would get a picture like this. So this is the identity on X tensor Y plus Z, right? And so instead of this kind of horizontal seam that's mapping things together, you get this vertical seam that's sort of expressing the fact that X is connected to both of those guys. And I call it a Ziploc diagram because distributivity is like taking a Ziploc bag that's halfway open and just pulling it apart, right? Which I think is pretty cool. So distributivity unzips. And so what I really find interesting here, actually, though, is that if you do this, you can get some new kind of quote-unquote monomials that you didn't have before. So if we just sort of look at things from top down and think about a diagram that looks like this, right? So X, Y, Z, W. Oh, and I need, whoops. I should probably start with the beginning. U, V, W, X, Y. OK, well, if we unzipped it all the way, right, that would be U tensor V plus X tensor W tensor V plus X tensor Y, right? And so there's sort of these two partial factorizations that we can do. We can sort of factor out the V on the right between these two, but then there's like this thing still hanging around. Or we can factor off the X from both sides on here and leave this part hanging around. But when we move to this two-dimensional notation, we can represent that as something that's topologically connected. And I have no idea what that means, but I find it sort of very interesting and intriguing. It's somehow, there's like an atomic term here that we didn't have before, which seems kind of cool. OK, so I think now we're ready for flourishing. OK, so again, now let me try and sort of like wrap it back around to Topos. OK, so flourishing. And how do we get there? And what does it mean? I don't have answers to any of those, but I'm going to ask some questions. And I'm going to kind of go backwards, right? That's where we want to get to, but let's sort of think through at least some of the steps. And I'm not saying this is the right answer, but it's at least one path that we might try and take. So it's like flourishing. So that's sort of step 4. Step 3, and I've talked to some of you a little bit about this while I've been here, is about governance. Step 2, and this seems like kind of a curve, is about user interaction. And step 1 is dev tools. OK, that's quite a list. OK, so I'm going to start with flourishing, though. And I'm going to take it that you guys agree, maybe you don't, but I'm going to take it that you do, that flourishing requires the easier sharing of precise concepts. So you can think of this as models, not numbers. And not only that, but it needs to be easy, like orders and orders of magnitude easier. And this is, I think, both a normative claim, so it should be easy, right? We should be, if we're flourishing, then we can do this. And also a descriptive claim in the sense that we can't do without it. If we can't find a better way to share ideas, then we're not going to be able to overcome the sorts of challenges that face us. And so my thesis of Topos is that category theory can really help us think new thoughts, particularly collectively, together. And so sort of one of my inspirations in this line of thinking is Brett Victor, who some of you may know. So he's done a lot of work on sort of user interaction and I'm not even talking about user interaction yet, but he has done a lot of work here. And so this is from an essay he wrote called Up and Down the Ladder of Abstraction, and talking about how when you want to show things to people, you really need to connect them sort of. You can't just throw the abstraction at them. You need to start at that bottom level and sort of build them all the way up. And so in some sense, I take him as sort of my inspiration in what's possible. And I highly encourage all of you to go to his website. It's called Worry Dream. But just look up Brett Victor. And he's really changed my way of thinking about what's possible with digital tools and where we should be trying to head. And so I guess if you accept those kinds of things, then kind of we can, we should, and we must. And so some of the things that I talked about today, like what does that mean, JS? I put an acronym in my paper. I don't remember what it stands for. But the Kalman filter example, that one I know what I'm talking about. Right, it's that by simplifying the concepts that we're working with and sort of showing them to us in different ways, category theory really can allow us to think new thoughts or think thoughts that were harder to think about before. And if that's true, then that opens up the space of what's possible to think about. A big part of this, I think, is going to be fixing mathematics education, and we've sort of talked a little bit about that with some of you. And this is something that I would like to talk about more before I leave. So we'll follow up on that later. Some of the pieces of my talk, of course, really touched on that as well with the vector calculus. Algebra 1, I understand, is sort of where we lose the most people. And as I've been telling everyone that I see, we have a big advantage, right? So a constant a versus a variable x. In classical algebra, these are just denoted by using different ends of the alphabet. And we have different pictures, right? And so people who get lost at that step, we have something to show them that could really help them through that, I think. Relations was another thing. There's sort of a lot of non-quantitative math that category theory is sort of very rich in as well. OK, so that's flourishing. To get there, I think we need to, and not just these pieces of flourishing, but flourishing in general, we need to work on our governance, our collective decision making. So obviously this is pretty true in politics. I'm not even going to go there. But it's true in policy too, right? So even sort of more bloodless policy, where we have like lots of sharp cutoffs that cause unnecessary suffering and also discontinuities in all of our models. And even more than that, just like default behaviors and sort of basic, like the basic incentives that are set up in systems, we're not thinking hard enough about formalizing those and sort of setting out the parameters of our governance. I think we want it to be better informed and more precise, possibly decentralized and parallelized, although that's maybe up for debate. There could be huge savings by making these kinds of services more efficient and less captured. So depending on who you think is doing the capturing, maybe it's the government, maybe it's the rapacious corporations, but most people agree that like something has captured our government, or our governance, I should say, sort of the way that we live our lives, which is not all government or all corporate by any means. And so really, I think we need better tools to formalize these governance systems. And people already have these tools, right? They use and/or diagrams and flowcharts and all kinds of things, but they're designing them ad hoc and making them up without the rules. And so we have some guidance to give and sort of how to do these things that they already want to do and are already doing in the right way. And so I forgot to mention it. Oh, let me, no, never mind. OK, so that's governance. OK, so now user interaction. How did we get to there? Well, if you think about it, it really is increasingly the case that governance is the province of whoever owns the users. So Google, Facebook, Amazon, Apple, the IRS, public education, these people have locked-in customer bases, and that is in many ways the source of their power. So Ben Thompson at the Stratechery blog, if you guys don't read this, you should also read it. So he basically theorizes about Silicon Valley and sort of the dynamics in Silicon Valley. And so the idea is sort of you want to be the funnel that's connecting the users to some kind of homogenized product like computational modeling. Evan. OK, so now user interaction. Well, Facebook and Google, they're pretty big. We probably don't want to fight them. The sort of next up and coming wave. The next up and coming wave sort of behind that is often services. So you think of things like Salesforce, Stripe. There's a bunch of sort of up and coming companies that are really building infrastructure as opposed to the, what's that? No.
Notion.
Indeed. And so, well, we'll get to that in just a second. I guess what I'm really looking at here, though, is Poly as a foundation for managing and defining these user dynamics. And I think it is extremely, or would be extremely valuable just at the level of UI and like building websites. But also, if you own the user and they're interacting with your website, then that prepares you to manage their governance. And so by getting the user sort of in front of your product or your, here we're not quite thinking about a product so much, but more like an open ecosystem. Having sort of that in place gives you some leverage for pushing on the governance. So dev tools. OK, so now, first step, we need to focus on the dev tools, because if we can help the developers create good experiences, they will bring the users. And so sort of a very first pass attempt, and you probably know that this thing already exists, and something I'm saying is stupid, but would be something that would automatically generate things like configuration drop-downs or right-click menus that developers have to put a bunch of sort of like stupid time into, because they know what they're doing, and it's a matter of like, there's some combinatorial information, some relatively small amount of combinatorial information, and then they have to like put that into the right place in the JavaScript library, and that's a pain. Let's see, so we really need to develop tools to help sort of create these dynamic interactions. So here I talked about these bubble derivatives, and it's not that these bubble derivatives need to replace the traditional notation, and they're not going to replace like three-dimensional graphs. What we want is we want all three of those things on the screen at the same time, so that the user can manipulate any of them and sort of see what happens in all of those places. So that's, again, something that I'm getting from Victor. OK, so my dream really is that I or someone else should be able to sit down and create some new graphical language and build a semantic interpretation of that language using methods like functor categories or Kleisli categories or whatever I want to use. And then I define the appropriate semantic mapping, and then I press a button, and it sets up a website for me that other people can come and use. And I don't have to build the web server. I don't have to do any of that stuff, because that's actually not what I'm putting in, for the most part. It wouldn't be that simple, but I think that's what we should be aiming for. And so now I'm going to be really presumptuous. So you asked me when we were talking earlier about sort of where could Poly go? And I think that a project like the kind of thing that I'm describing, really sort of even back here, it really needs some kind of a seed to start around. And if you want it to be, and you sort of tried to pull people in to do it, then maybe Poly could be that seed. The way I think of it, the kinds of things that you would need to work on for a seed like that are some kind of semantic markup language that is going to replace LaTeX. Right? The fact that we're still using TeX is bad. And if we really want to be able to write down sort of interactive visualizations that people can use on the internet, extending LaTeX is probably not the right way to go. And so this also ties back to the math folder project. So having some kind of more semantic description of the symbol, right? So up at the front of your tech document, Semantic, you declare a bunch of variables, right? And you say what their types are, and you reference, some OWL ontology or whatever kind of machinery we'll want to point those to. And now that helps with this kind of math folder project too, where if you can get the authors to start putting this in as they're writing it, then there's much less work to do sort of down the road. We need lots of libraries for visuals and computation, so you guys are already hard at work on this. Lots of default settings, right? So much of me not being able to set up a web server is that I just don't know the proper incantations to stick in. And so we need experts from those fields to come and help us and say, well, here's the easiest way to set that up. And if it blows up on you after you've got that set up, then maybe tweak these things. But let's start simple. OK, so now I'm almost done, I promise.
You heard of no code?
A little bit.
That's basically what you're saying, like setting up websites that code.
Yeah, but I guess that's the thing, right, is how are you going to do that if you don't have an extremely sophisticated system for describing your user dynamics?
Right.
You're only going to be able to set up very simple systems, but we have sort of much better tools. OK, so now I'm just going to close. I'm going to, I'll come back here. I'm not going to get all the way up to Flourishing, but I want to sort of talk about how I think these three guys kind of fit in with Poly. And for each of them, there's kind of like there's an instance level version and there's a generic version. And as a community, when we start building things, I'm on the fence, and probably you have a lot more insight than I do about this. But I feel like it's going to be very important for us to eat our own dog food. And so I think in some ways, Poly can sort of fill in all of these pieces. And so in terms of governance, right, we're asking, how do we run this project? Right, this Poly project, right? Here are the things we need to here are the things we need to keep track of. And sort of as we're doing that, we kind of figure out how do we run a project. Because that's how category theorists do things, right? OK, well, that's good. OK, so now what about user interaction? So now we're asking, how do we want to share Poly with people? Right? What are the things that we want to show them to make them understand? And of course, the follow-on, right, is just how do we share sort of structured concepts more generally? And for dev tools, so now, right, we're trying to share some concepts with people. So now for dev tools, the questions we want to ask is sort of, how do we want to elicit this material from ourselves? Right? What do we want to have to write down to make this show up out in the world? From ourselves. And I'm not going to try and write out the other one, but of course the next one is going to be from others. I think that's it.
Question?
You possibly could.
When you say, this is obvious,
Yeah.
when you say how do we elicit this material from others, you're asking what should dev tools?
Yeah, so I'll use this example that I've already showed Owen like twice today. So I've been talking about scheduling a little bit recently. And so in the sort of very simplest version of scheduling, you have a collection of jobs, a collection of machines, and a collection and a duration for every pair. And so you say, how long has this job got to run on this machine? And for the simplest one, there's no order or anything on it. And so this is a schema for me, right? I want to describe that as a schema. And this is all I want to write down. But when I do that, now I really have to unfold it because the actual schema looks like this. And then there's this like additional constraint, cone, right, P, J, M. And so now when I want to start filling this guy up, right, I throw in a couple J's, J1, J2, J3, M1, M2.
What's P?
P is the sort of generic object which is supposed to be standing in for this product. But sort of in the sketch formalism, right, you get a category and then you get some collection of cones sitting on top of that category. And so now I put in a couple of these guys, and now I have to somehow invoke this constraint cone in order to fill up the set here, right? I need the product, and then I have to sort of fill in the details. Doing this in a Connexus in CQL is a super pain in the butt, let me tell you. Because one of the reasons you don't have any names for the things in here. And so you have to refer to them by the pairs of their projections and like add these things in. And so it's great, right? You want all of this declarative machinery for the computer because that's what it needs to read in order to get everything right, but you don't want the user to do that. And so when I ask about how do we want to elicit these things from ourselves, I mean, I want to write this and I want the computer to figure out all this crap for me. And more than that, I actually want it to govern the interaction, right? I want to put these things in, and then I want it to tell me, oh, you better tell me what this is. And so when I put new things in, it comes back and asks me questions and guides me through filling it up. That's what I mean. Is too much. You can't get like an anvil dropped on your head and then ask a question.
Well, I have many questions, so that's
That's right.
Yes, thanks, Spencer, again. Thanks.
Thank you.